Today we are covering BagelVLA, enhancing long horizon manipulation via interleaved vision language action generation.
A really interesting one. This is coming out of Tsinghua University and ByteDance Seed.
And the big idea here seems to be this new unified framework they've built. It's meant to break down the walls between high-level reasoning and low-level control.
Right, using something they call interleaved planning. So instead of just mapping an instruction to an action, BagelVLA first generates a text plan.
It thinks in words first.
Exactly. Then it imagines the outcome with visual forecasting, and only then does it actually generate the robot's action.
And the big technical piece that enables all this is a mechanism they call Residual Flow Guidance, or RFG.
That's the core of it. It takes the current image, adds a bit of noise, and then predicts the future frame in a single step. It's incredibly fast.
Fast and stable. It brings latency way down, and the results...
Well, they're outperforming state-of-the-art models like Zero and VPP. Especially in these really complex long-horizon tasks, like getting a robot to solve a math problem using actual physical blocks.
Which is just incredible. I think for anyone listening, this really feels like a big step towards solving that brain-body disconnect in robotics.
I think so, too. It's a huge problem.
Let's jump right into that disconnect.
Yeah.
Because when you look at the field now, you know, models like RT2, OpenVLA, Octopus, you see these amazing demos.
Oh, for sure.
But this paper's argument is that there's a fundamental flaw in how we're building them. What's the specific problem BagelVLA is trying to fix?
Well, the problem is that we have all these great modules, but they don't really talk to each other in a deep way. It's modularity without real integration.
So you have one camp with models that have incredible brains.
Right, your VLMs. They're amazing at linguistic planning. They can look at a total mess and generate a perfect step-by-step plan. First, pick up the sponge.
They get the what? The semantics.
Precisely. Then you have another camp with models that have great eyes, so they're good at predicting what happens next in a video. And then you have the policy networks, the hands, which just kind of mimic trajectories.
So the brain tells the body what to do and then just, clocks out.
Sort of, yeah. The feedback loop isn't tight enough. And the result is that these models totally fail on long horizon tasks.
Okay, give me an example.
If you tell a standard robot, stack these blocks in a specific order, blue, then green, then orange, it might get the blue one right.
But then it gets lost.
It loses the thread, it forgets the plan, or it can't visualize the state it needs to be in to get the orange block on top of the green one.
It's just reacting, not executing a full vision.
Exactly. And that's the paradigm shift with BagelVLA. It argues you can't treat reasoning, predicting, and acting as separate things. It interleaves them. It's thinking, imagining, and acting all in one continuous loop.
Okay, I want to get under the hood of this unified framework because, you know, that term gets thrown around a lot.
It does.
Structurally, this isn't just one giant neural network, is it?
No, not at all. And that's a really crucial engineering decision. They use what they call a mixture of transformers, or UNOT. It's basically a system that connects 3 different expert models using self-attention.
Okay, 3 experts. Let's break those down. We've got an understanding expert, a generation expert, and an action expert.
Right. So the understanding expert is the brain. It's a 7 billion parameter model based on Qwen 2.5.
Okay.
And its job is the text, the linguistic planning. But here's a key detail for the technical folks listening. It uses SIGLITE2 for the visual encoding.
Not standard CLIP. Why SIGLITE2?
It's just so much better at fine-grained detail. You know, if a robot needs to tell the difference between 2 types of screws, CLIP embeddings might blur that together. SIGLIP keeps that detail sharp.
Got it. So that expert looks at the scene and generates the plan. Locate the blue block.
Yep. Then it passes that to the generation expert.
Which is also 7B parameter.
Also 7B, also Qwen-based. But it swaps out SIGLIP for the VAE from FLUX.
Ah, FLUX, the open weights image model that's been making waves.
The very same.
Yeah.
This expert is the imagination engine. It takes that text plan from the first expert and generates a picture of what the world should look like after the action is done. It's visual forecasting.
And then we get to the action expert. And this is where I saw a huge size difference. The first 2 are 7B, but this one's only 2 billion parameters.
Yeah.
Why so much smaller? I mean, this is the part actually moving the robot, right?
Yeah.
Shouldn't it be the most powerful?
You'd think so, but it's a very deliberate choice about latency and control frequency. To get smooth robot motion, you need to send updates very, very fast. We're talking 40, maybe even 70 hertz. A 7B model just can't run that fast for every tiny movement. The robot would be incredibly jerky.
So keeping it small lets them run it fast.
Exactly. With a 2B model, they can use things like KV caching and just fire off those motor commands super quickly. It lets the system be smart, slowly, planning every second or so, but move quickly, updating 50 times a second.
That's a great way to put it. It's asynchronous. Your brain doesn't consciously think about every single muscle fiber firing.
That's the perfect analogy.
But okay, what about the latency on the visual side? That's always the deal breaker. Generating images is slow. A robot can't just pause for 5 seconds to dream up the future before it moves.
No, it can't. And that's the central bottleneck. Most methods start with pure random noise, pure static, and then they slowly denoise it over many steps to create an image. It takes forever.
So how does BagelVLA solve this? This is the Residual Flow Guidance thing.
This is the RFG, yeah. It's the secret sauce, and it's actually brilliantly simple. Instead of starting from static, it initializes the generation with the current video frame, plus just a little bit of noise.
Oh, I see. So it's not asking the model, hey, draw the future from scratch. It's asking, how is the current picture going to change?
Exactly. It's only predicting the residual, the delta. And because the starting point is already a real image, the model doesn't have to waste all its compute power redrawing the table, the walls, the background.
It just focuses its compute budget on the robot arm moving and the block shifting.
Correct. And because that change is a relatively small part of the image, it can do it with single-step denoising, just one step. No need for 50 iterative steps. That's what gets the inference time down to about 1.2 seconds on a high-end GPU.
1.2 seconds. That's still a noticeable pause, but for high-level plan updates, that's totally within the realm of possibility.
It is. And remember, that's for generating a whole chunk of actions. The actual execution of that chunk is happening much, much faster.
There's another huge benefit here that I noticed, which is stability.
Yes. This is a classic problem with video generation. The models hallucinate, the color of the wall might change, or an object in the background just disappears between frames.
Which would be catastrophic for a robot. If it imagines the table isn't there anymore, it might try to drive its arm right through it.
Absolutely. But with RFG, because it's starting from the actual pixels of the current frame, the background stays locked. It's perfectly stable. It's a massive boost for reliability.
I want to shift gears to the data. These models are famously data hungry, but good robot data is really hard to come by.
It is very scarce.
You can't just scrape the web for it. So what was their strategy here?
They used a massive hybrid data set. They took general visual question answering data, which is plentiful, but more importantly, they used human videos from a data set called EgoDex.
So like first-person footage of people just doing things with their hands.
Yes. But here's the really clever part. You can't just show the model a video of a hand picking up a cup. It needs to learn the reasoning behind it. So they used another AI model, specifically something called Seed 1.5VL thinking, to annotate all that human video data with synthetic text.
So they used an AI to teach another AI how to think.
Pretty much. So now the model isn't just seeing a hand move, it's also reading a synthetic internal monologue that says, my goal is to pick up the cup, so my first step is to reach for it.
That's incredible. It's injecting intent and causality into what was just observational data.
It completely changes the game. It turns simple imitation into something closer to understanding.
So walk me through the training process. How do you actually cook all this together?
It's a two-stage recipe. Stage one is pre-training. This is where you only train the brain and the eyes, the understanding and generation experts.
No actions yet.
No actions, just training them on that huge data set of human videos and VQA to understand the world and predict how it changes. It's like sending the robot to school before you send it to the gym.
I like that. So stage two is the gym.
Stage two is the gym. That's the fine-tuning stage. You bring in the 2B action expert and the actual robot data sets, Agibot, RoboTwin, and so on. And now you train all three tasks: plan, forecast, and act all together end to end.
Okay, let's get to the results. The architecture sounds great, but does it actually stack blocks better than everything else?
It does. In the Kelvin benchmark, which is a standard for these long horizon tasks, BagelVLA achieved an average completion length of 4.41.
And how does that stack up?
It beat VPP, and maybe more importantly, it beat zero. And crucially, in the RoboTwin benchmark, it performed really well in the unseen setups where they randomize the environment. That shows it's actually generalizing, not just memorizing.
But the real test, the one that I think makes this paper so compelling, is the real-world hardware experiment.
Oh, the math problem.
The torture test on the AgileX dual-arm robot. Tell everyone about this because it's wild.
It's my favorite part of the paper because it really proves the whole system is integrated. So you have the robot, a table, and a bunch of blocks with numbers on them.
Okay.
And the instruction isn't, pick up the block that says 4. The instruction is complete the equation 4 plus 6 equals 0.
Whoa! So the robot has to do the math first.
It has to do the math. It has to read the numbers, perform the addition in its head, realize the answer is 10, and then search the table for the 1 block and the 0 block and place them next to each other.
That is an insane chain of reasoning that has to survive all the way down to the motor control.
Yep.
It is. Your standard policy network can't do math, and your standard LLM can't move an arm. This thing does both in one shot.
So what were the success rates on that?
This is the interesting part. The planning accuracy, did the robot correctly figure out that it needed a 1 and a 0 was almost 90%.
So the brain is working perfectly.
The brain is working perfectly, but the actual physical success rate was lower, around 63% to 73%.
So it knew the answer was 10. It went to grab the blocks, but maybe it just fumbled one.
Exactly. A classic case of butterfingers. But, and this is the key context, the next best model, 0, was only getting around 40% on similar tasks. So jumping to 63% is a massive leap forward.
That gap, though, 90% planning accuracy versus 63% physical success. That's fascinating. It really suggests that the intelligence problem is maybe getting close to solved. The robot is smart enough.
It's the planning versus execution gap. The reasoning is there. It's the fine motor control, that last mile of translating the imagined future into precise torques and forces. That's still the bottleneck.
It makes you wonder if the limiting factor is even software anymore. Are we just waiting for better hardware, better servos and grippers?
It's a very real question. We're kind of writing software checks that the robot's body can't quite cash yet.
Okay. I want to wrap up with a final thought on this idea of hallucination. In the world of LLMs, we treat hallucination as a bug, right? Something to be stamped out.
Absolutely, it's the enemy.
But this paper basically says that for robotics, hallucination or, visual forecasting is a core feature.
It has to be a feature. A robot needs to hallucinate the future. It has to be able to imagine a world state where it has successfully completed the task. If you can't imagine holding the cup, you can't figure out the path to get there.
But it has to be a constrained hallucination.
That is the entire point.
Right.
Unconstrained hallucination is just noise. Constrained hallucination is planning. And that's why RFG is so critical. It grounds the dream in the reality of the current pixels. It's basically telling the robot, dream about a future, but keep your feet on the ground.
Dream about the future, but keep your feet on the ground. That is the perfect summary.
It really is.
This paper is an absolute must-read for anyone in this space. The residual flow guidance idea alone is worth it. We'll have the full paper linked in the show notes.
I'd also say check out their architecture diagrams for the mixture of transformers. It's a really elegant design.
Well, thanks for tuning into this breakdown. Keep building, and we'll see you on the next one.
Take care.